So the left-hand estimate, we assume that the rate on the left is the constant rate for the small time interval. A right-hand estimate, we assume that the rate on the right is the constant rate for each small time interval. The overestimate is going to be the larger number from your left and your right-hand estimates. Your underestimate is going to be the smaller number from your left and right-hand estimates. It's not always the same. So whenever you're talking about over and under estimates, you have to compute both the left and the right and then compare the numbers you get. For our variables, we had delta t. So delta t was these small time intervals we were looking at of measurement. In the last example, delta t equaled 2 because we were counting by 2's. N was the number of rectangles that we're using to estimate a function. And now we're going to add on a and b. So a and b are going to be the starting and ending point of a function defined by its independent values. So where are we looking between what two values? That's your a and your b. We'll see why those are relevant in a minute. So if we want to make our estimate better, right, so that we don't have as much over or under, how do we do that? So let's look at another example. Suppose that during this bicyclist racing down the flat road, we had the ability to measure the velocity every 1 second instead of every 2 seconds. How does that change our estimate? Is it better or worse? So let's take a look at this table and let's talk about some of our new variables. Let's start with delta t. So remember last time delta t was 2 because we were counting by 2 seconds. Here, my delta t equals 1 because now I'm counting by ones. I was able to measure every 1 second. My a is going to be my starting point, so that's 0. My b is going to be my ending point, which is 10. And then my n, which is the number of intervals that I'm going to be using, I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I can count them by looking between how many points I'm going to be using. But I also have this relationship that b minus a divided by delta t equals n. Similarly, I can use that b minus a divided by n equals delta t. So if you know the length of your interval, so here b minus a is 10 units long, so b minus a is 10, and you know either your delta t or your n, you can use that to find the other one if you need it for some reason. So again, we want to do a left-hand and a right-hand estimate. So let's start with the left-hand estimate. Okay, so our first estimate, we're considering what happens between 0 and 1 seconds, and we're going to pick the rate on the left for each one. So we're going to do 0 times 1, rate times time, plus, now from time equals 1 to time equals 2, if we pick the rate on the left, we get 3 times 1, plus, from time 2 to time 3, I pick the rate on the left, 5 times 1, plus, 6 times 1, plus 7 times 1, plus 8 times 1, plus 10 times 1, plus 12 times 1, plus 15 times 1, plus 18 times 1. Now, you may be wondering how I was able to go so quickly, but I want to remind you that if we're always picking the rate on the left, that we're going to use every single rate except for 22. So I was just going down the list and writing down the rate and multiplying each rate by my delta t. And I knew that I could use all of them except for 22 because 22 is the rightmost point. So again, I need to add up all of these numbers to get my left-hand estimate. When I add up all these numbers, I'm going to get 84. And remember, my units are going to be in feet because each of these was the rate of feet per second times seconds. So my left-hand estimate was 84 feet. If I do the same thing now for the right-hand estimate, for each 1 second interval, I'm going to pick the rate on the right. So I'm going to use every single rate except for 0 because that's the leftmost rate. So I have 3 times 1 plus 5 times 1 plus 6 times 1 plus 7 times 1 plus 8 times 1 plus 10 times 1 plus 12 times 1 plus 15 times 1 plus 18 times 1 plus 22 times 1. So if I add these all up, don't forget my times 1 here at that 18. If I add those all up, I'm going to get 106 feet. So I want to remind you that in the previous problem, when delta t equaled 2, n equaled 5, our bounds were 74 to 118. Now our bounds are 84 to 106. Those are improved bounds because the lower estimate has come up from 74 to 84 and the overestimate has come down from 118 to 106. So I have more accurate information than what I had before. And again, now if I was going to do my best estimate, I'm going to do 84 plus 106 divided by 2, and that's going to give me 95 feet. So last time my estimate was 96 feet. This time it's 95 feet, still relatively close. So this is a better estimate. Let's look at the picture to see how it's changed. So again, we're graphing our rate versus our time, only now we're doing it every 1 second instead of every 2 seconds. And again, I can get a general idea of what the function is doing by connecting these left and right hand points. What you should notice here is that there's less of an overestimate than before. Because the rectangles are smaller, there's less area that's causing us an error. So again, the left-hand estimates are in orange and the right-hand estimates are in blue. So the overestimate has come down a little bit and the underestimate has come up a little bit. But what did we change, right? What did we actually change within the problem? Because we still looked from 0 to 10. So what changed was our delta t and our n, okay? So our delta t got smaller. So our time interval that we were measuring got smaller, which meant that n got bigger. So if you can make delta t smaller, or if you can make n, the number of rectangles you're using, more of them, your estimate's going to get better, right? So the idea is that, let's say we could measure every half a second or every quarter of a second. Eventually these rectangles get small enough that they're essentially a line that hits the function. And the error is gone. The overestimate will come down. The underestimate will come up. And that is our goal here. Because the more accurate we can make our estimates, the better off we are in finding our area under the curve. So far we've been using tables. But let's take a step back and do a couple of examples and see how we apply this using our n, our delta t, and our estimate techniques. Example 4. The figure below shows the velocity of an object over 31 minutes. So remember, velocity is a rate and 31 minutes is a time. Part A. Estimate the total distance traveled using a left-hand sum with n equals 2, and part B will be to do the same, but a right-hand sum. So that means we want to use 2 rectangles to estimate the area under this curve. Now remember, the more rectangles you can use, the better your approximation is going to be. N equals 2 is not going to be a very good approximation, but we'll do it nonetheless. So remember, if we want to find out n or delta t, and we have the other one, we can use that b minus a divided by n equals delta t. I chose to use this form because I don't have delta t yet. If I had delta t and not n, then I would have used b minus a over delta t. So here, my b minus a is the length of my interval. So that's 31. My n is 2, which means my delta t is 15.5. So that means I'm counting by 15.5s, right? That's a little weird. So that means I'm starting at 0, and then 15.5, and then 31, right? So that's how I'm counting. And if I want to use n equals 2, that's how I have to split it up. So if I'm doing a left-hand sum, that means that the left-hand point of each rectangle is what is going to touch my function. So that means for my first interval, which is 0 to 15.1, I'm using the 0, which is the lefter of the 2 points, to figure out how high to go on my rectangle. Okay, so my rectangle is going to look like that. And then for the interval 15.5 to 31, I'm going to use the 15.5, which is the left of my 2 points, to get the height of my rectangle there. So my estimate is going to be the area of these two rectangles added together for my left-hand estimate. And again, if you look at the picture, you'll see it's the left-hand corner of my rectangles that's touching the function, because I picked the value on the left of my two possibilities to get my rate, right, which is the height. So if I look at my first rectangle, I know that the width is 15.5 because that's my delta t, and then my height appears to be 20. So I have to do 15.5 times 20, which is going to give me 310. So the area of this first rectangle is 310. Now for my second rectangle, my height is going to be based on the value I get when my independent value, which we'll call t here, was 15.5. So if I approximate the height here, I'm going to go back over here to the y-axis, I'm going to say that that's roughly 15. So 15 units high and 15.5 units wide. I multiply those together and I get 232.5 for my second rectangle. Adding those two numbers together is going to give me 542.5. So that's my estimate for part A, 542.5. And looking at these rectangles, I can tell that this is an overestimate for the area under the curve because there's extra area there. Let's see what happens when we use the same method to look for a right-hand sum. So now, when I'm looking for a right-hand estimate, that means that I'm going to use the height based on my right point between the 2 points to figure out the areas of my rectangles. So again, my first interval is 0 to 15.5. So that means I'm going to pick the height at 15.5 to draw in my rectangle, right? Because again, I need the right-hand corner to touch my function. Now, when I do this for my next interval, 15.5 to 31, that means I'm picking the height at 31, which is unfortunate because that height is 0, right? Which means that the area of my second rectangle is 0 because it has no height, which means it has no area. So that means I just need to get the area of my first rectangle here. So again, I'm going to do width times height. We said the width was 15.5. We approximated the height to be right around 15. And we said that 15 times 15.5 was 232.5. So for part B, I get an estimate of 232.5 plus 0, which was 0. And you can see here by the rectangles that this was an underestimate. There's huge chunks of area missing if I'm looking for the exact area under the curve. So again, we can see that these estimates are terrible, right? They are way off. The overestimate was way too high. The underestimate was way too low. And that's because n was really small. The bigger we can make n, the better our estimate will be. But now if we have a function and we have an n, we know how to draw in our rectangles so that we can estimate areas. Let's look at another example. Example 5. If t is in hours of a 20-hour period, the rate at which bacteria population growing is given by f of t equals 3 plus 0.1 t squared. Find an over and under estimate of the total change in bacteria over this period if delta t equals 4. So we want to approximate the area under this curve. This curve is the rate at which the bacteria population is growing. So if we were to find the area under the curve by estimating using rectangles like we have been, that should tell us the total change in bacteria. Again, it's not going to tell us how many bacteria we have, but it'll tell us how much it's changed by. Now, if delta t equals 4, what do we know about n? So a 20-hour period, that tells me that b minus a is 20 because that's the length of my interval. So I have b minus a over delta t is going to give me n. So if I have a 20-hour period and I divide by 4, that means I'm going to be doing 5 estimates. N equals 5. Delta t is important because that tells me how I'm going to get from time equals 0 to time equals 20, right? Because it's a 20-hour period. So delta t equals 4 means that I'm getting there by counting by 4s. So what we need to do now is we need to set up a table so that we can find the left and the right hand estimates. And since delta t is 4, we're counting by 4s. So 0, 4, 8, 12, 16, 20. It's a 20-hour period, so we stop there. So remember, we put our independent variable on top and our rate in the bottom, right? Which means we need to take each of these numbers and plug them into f of t. So plugging each number in, we get 3, 4.6, 9.4, 12.4, 28.6, and 43. Now that we have our table, we can find a left-hand estimate and a right-hand estimate and use that to find our over and under estimate. So the left-hand estimate, remember we're going to use every single rate except for the rightmost. So we're not going to use 43. So I'm going to do a little algebra trick here. And since I know that every single rate will be multiplied by 4, because these are 4 units each, I'm going to pull the 4 out front. So 4 times 3 plus 4.6 plus 9.4 plus 12.4 plus 28.6. If you're more comfortable multiplying each one by 4 individually, that's fine. It means the same thing. So when you crunch this number, you get 232 bacteria. When we do a right-hand estimate, we don't use the leftmost point. So again, I'm going to pull the 4 out front, my delta t, and I'm going to have 4.6 plus 9.4 plus 12.4 plus 28.6 plus 43. So all the rates except for my leftmost rate. I multiply those together and I get 392. So now again, I need to look at my two numbers and the bigger one is my overestimate. So 392 is going to be my overestimate and 232 is going to be my underestimate. If for some reason this question had asked for best estimate, we would have averaged those two numbers together and we would have gotten 312. So we can see that the change in bacteria is positive, but we don't know exactly how many bacteria there are because we don't know how many we started with. But we have a general sense of how much it's changed over this 20-hour period. So the difference in this problem, again, was that we had to set up our own table instead of having one provided to us. And we were able to do that by figuring out our values for t using the delta t and your interval, b minus a, and plugging them into the given rate to get the corresponding rate values.